Hello, and welcome to our presentation on transform densities. Today we're going to describe what transform densities are and how they can be utilized. To understand what they are, we must first understand what probability densities are. Probabilities are used in combination with a discrete random variable. A discrete random variable is, for instance, an event that can be labeled, an event that is countable. An example of this would be the rolling of a die. This is a distribution of a probability. So we have a die, and we roll it, and the probability, for instance, of it rolling 2 is 0.22. And the sum of all these probabilities amounts to 1. Probability densities are used when events are uncountable. So this is in combination with continuous random variables. An example of this would be the amount of rain over a certain time period. This graph describes the probability of a variable taking a value in a certain interval, the interval being 2 to 6 centimeters, for instance. So this calculates the probability of the rainfall being between 2 and 6 centimeters. We cannot calculate the probability of one given event in this continuous graph because the probability, let's say, of the rainfall being exactly 2 centimeters is 0. It could be 2.00001 and then it's not exactly 2. It could be 1.99999, which is not exactly 2. Therefore, it never really takes on the value 2 centimeters of rainfall. Because of this, we need to define an interval. So here we define the interval between 2 and 6, and everything between these two values of 2 and 6 is counted. And from that, we calculate the probability. The integral of negative infinity to infinity on the x-axis needs to amount to 1. Now, when do we use transform densities? We use them whenever we observe something indirectly and the variable or factor of interest is hidden. We only have the probability distribution of the underlying factor, but we don't know what it looks like for the factor that is of interest. Examples of this in cognitive science are visibility of a stimulus given a certain noise level. So we have a certain noise level, and we want to calculate how likely it is for that image to be recognized and transformed into a coherent thought or image. Same goes for hearing and linguistics, or EEG signals. So our experiment outputs a random array of information, and we try to make sense of that information based off of the variable that is of interest. On to the mathematical components. What we have is the probability distribution Px of x. An example of this would be the amount of rain over a given time period. What we also have is the transfer function, gx, that describes the relationship between x and y. What we want to know is the probability distribution py of y, given px of x and gx. In combination with the rain example, this probability distribution could describe the probability of the production of mud. So how do we transform densities? Step 1 is to check whether the transfer function gx, which explains the relation between both variables, to check whether that is strictly monotonic on the interval of interest by computing the derivative of gx. We will do this later in an example. Then we compute the inverse function of g so that we can substitute x by y. An example of this is shown here. Step 3 is to compute py of y by substituting x by y using the inverse function and multiplying with the derivative of that inverse function, as seen here. The colors show what's what. In step 4, we suppose that px of x is approximately normally Gaussian distributed. This is the Gaussian formula on the left, px of x, and we turn that into py of y by plugging in the inverse function where x is substituted by y. So now we come to the question of why. Why do we even need any of this, and why does it make sense? Why do we need these steps? Why does g of x have to be strictly monotonic? Why do we have to compute the inverse function? And why do we have to multiply with the derivative of that inverse function? Makes no sense, right? Wrong. Here's why. So now we try to represent this transformation in one graph. This is the graph, and we want to transform px of x to py of y. We want to, let's say, transform the probabilities between the interval of 3 and 5 onto the y-axis, and we do this with the help of the inverse function of g of x, as you can see here. So we map all of these probabilities from the x-axis to the probabilities on the y-axis. So as you can see, the interval width may vary depending on the slope of g of x. For the first question, why does g of x have to be strictly monotonic? This is because, let's say, the slope of the inverse function of g of x is 0 on the interval between 3 and 5. Then we would map a lot of probabilities on the x-axis, a lot of values, onto the same value of y. This should not be done because there won't be unique mapping. So the second question is, why do we have to compute the inverse function of g? This is because, as you can see in the diagram, it maps all probabilities of x to all probabilities of py. It gives the relation between the two. Coming to the question of why we have to multiply with the derivative of the inverse function of g of x. So for this, we look at the yellow marked interval. On the x-axis, the width is 2, so it is pretty wide, and this width is, with the help of the inverse function, mapped onto the y-axis. But as you can see, because the slope is not steep enough, it is mapped on a way more narrow interval. To account for this disparity, we have to multiply with the derivative of the inverse function of g of x, because else the probabilities would not stay the same. So for this example, when we multiply with the derivative, the density increases when it's mapped onto the y-axis to make the probabilities stay the same. So the probability density adapts to the width of the interval when we multiply with the derivative. At an instance where the slope of the inverse function of g of x is 1, the widths are the same, as shown in the green interval. Here, the probability densities stay the same, so we multiply by 1. Now, we will explain how a probability distribution may be transformed with the help of an example. Let's say you're at a party. X is the number of guests at that party, Y is the number of drinks, P of X is the probability distribution for the number of people, G of X the relation between the number of guests and the number of drinks consumed, and P of Y the probability distribution of drinks per person. P of Y is what we are looking for. We want to transform P of X into P of Y. The first step, as you know, is to check whether G of X is strictly monotonic. What we have is Px of X and the relation Gxy equals x squared. What we want is Py. To check if g of x is strictly monotonic, we must calculate the derivative of g of x to find the slope. The derivative of x squared is 2x. Now we see the difference between what a monotonic graph may look like and what a strictly monotonic graph should look like. On the interval x greater than 0, 2x is strictly monotonic. In step 2, we compute the inverse function of g of x by taking the root of x. Hence, x is equal to the root of y. In step 3, we substitute x by y and multiply with the derivative of the inverse function of g of x. Here, we define p of y as p of x, and instead of x, we plug in the inverse function. We multiply with the derivative. This value needs to be positive. This is why we use the absolute value. Else the probability will be wrong. Now to define p of y, we plug in the value we calculated in step 2 into px and multiply this with the derivative of that value. So in step 4, we assume that our example is normally Gaussian distributed, and we express this with this function. X is later to be substituted with the inverse function that we calculated. So we express p of y with p of x and the inverse function multiplied with the derivative. And when plugging it into the Gaussian formula, x is substituted by the root of y, which is our value that we calculated. So now we have successfully transformed the probability distribution for the number of people with the help of the relation g of x into p of y, which is the probability distribution of drinks per person. We can use a graph to help express this function. And that was our presentation. We hope you understand what probability densities are and how you can transform them. Good luck.